Good morning, everyone. My name is Narong Boonsirisumpun. I'm a PhD student in Information Technology from the Faculty of Informatics, Mahasarakham University. Today, I'm here to present my research experiment on the topic named Fast and Accurate Deep Learning Architecture on Vehicle Type Recognition. The outline of my presentation today is right here. First, we're gonna talking about the introduction and the background of the problem. Second, we're gonna talking about the method we use in this experiment. And then the dataset, experiment and result, and finally the conclusion. For the introduction, the vehicle image recognition is one of the challenging problems of the world. Because in every day, there are a lot of the vehicles that passing through the video surveillance image. And for some security reasons, most of the video surveillance image, they are trying to detect the vehicle position in the image and then extract the detail of that vehicle out from the license plate, like in this example. But however, in many situations, the license plate does not appear clearly in the scene. Like in the example, sometimes the license plate is hiding from the scene because of the orientation view of that vehicle, or sometimes there are some objects that blocking the license plate from the image. In some situations like this, the system needs to look for other details of that vehicle instead, such as the vehicle shape, the vehicle model, or the vehicle type. That's what we are focusing in this research. In our research, we are focusing on the 5 popular types of vehicle using in Thailand. The first one is sedan, and then hatchback, SUV, pickup, and the van. From the detail we mentioned in the introduction, in this research, we are trying to solve the vehicle type image recognition based on those 5 vehicle types, using the method in deep learning technology. A deep learning is a successful technique based on a deep layer neural network. This method has gained popularity in many areas in the field of artificial intelligence, machine learning, and image processing. The main technique we are using in deep learning is the convolutional neural network, or the CNN. CNN is one of the most advanced algorithms for solving image recognition and image detection. There are several CNN models that we brought into our research. The first one is MobileNet. The MobileNet is the small size of the CNN model. It is a CNN model that intends to reduce the size of another standard CNN model for making it suitable to use in a mobile device by using the concept of depth-wise and point-wise separable convolution. The depth-wise and point-wise reduce the size of the convolutional layer, like in this example, but still achieve a good performance compared to other CNN models. The second small size CNN model we use in our research is MobileNet version 2. It is a new version of MobileNet, but with additional 2 improvement concepts: the linear bottleneck and inverse residue block. The linear bottleneck is a special layer that adds into the standard depth-wise separable to capture a transformation if there are some of non-zero values that still remaining, like in this picture. And then they add another special connection called the inverse residue block. It is the block that tries to connect the depth-wise separable into the previous bottleneck layer, but using the thinner layer instead of the thick one. MobileNet version 2 It a bit smaller than the first generation, but still had an equivalent performance. MobileNet version 1 and version 2 are the small-size CNN models that we first chose to use in our vehicle-type image recognition problem. And then we compare it to the full state-of-the-art models such as VGGNet and GoogleNet. For VGGNet, we include both VGG16 and VGG19 into our experiment, and then we also include the GoogleNet, Inception, version 3 and version 4 to challenge with the MobileNet. We also include another CNN models that have the residual connection block inside, as same as MobileNet v2. We choose ResNet 50 and Inception ResNet version 2 in this case. And finally, we choose the Darknet 19 and Darknet 53. This is the backbone model inside the popular and fast YOLO algorithm to compare the MobileNet in terms of the speed. So, totally, we use 8 CNN models in our experiment. For the dataset, we create 2 datasets on our vehicle type image. We name it VTID dataset. The first dataset has 1310 images with 5 classes of vehicle type, including sedan, hatchback, pickup, SUV, and finally, it's unfortunately that we cannot collect enough data on the van vehicle, so we include another type of the vehicle such as motorcycle into this 5th class and rename it to other vehicle. That first dataset is used for testing the effect of the small size data. Then we expand more images in our second dataset, the VTID2. This newer dataset has 1456 images, with 1200 plus of images in the sedan and pickup class, and 600 plus in other 3 classes. After creating VTID2 dataset, we add 5 data augmentation in that dataset to create more data in the experiment. Then, the result we have 5 more sets of training data. VTID2 horizontal flip, VTID2 random shift, VTID2 rotation, VTID2 zoom, and VTID2 brightness. In the experiment, we split our experiment into 3 parts. The first experiment is only on the MobileNet. In the experiment 1, we use VTID1 dataset with 1310 images. The evaluation process using the tenfold cross validation to calculate the accuracy of vehicle type image recognition. The method using only on the MobileNet version 1, but including 2 parameter tuning, the width and the resolution multiplier. The result on experiment 1 show in table 1 and table 2. We found that the base of both parameters is the highest value of their choice. The base for width multiplier is 1.0, and for the resolution is 224 by 224. Both of them give the highest accuracy at 93.4%. We also make the experiment on every combination of the resolution and the width multiplier. We still found that the 1.0 width and 224 resolution is the best match for our VT81 dataset. Table 4 shows the confusion metric of MobileNet prediction on our VT81 dataset. The highest error type of vehicle was SUV, with the lowest accuracy of only 70 and 54%. The main mistake of the SUV type because it had more shared similarity in shape to other three vehicle types, such as pickup, hatchback, and sedan, specifically on pickup and hatchback, because they have the front and the side shape that look like the pickup and the rear shape that look quite similar to the hatchback. After we found the best parameter of MobileNet in our dataset, we move on to the experiment 2. In this part, we still use the VT81 as the main dataset, but we include 4 other CNN models to challenge MobileNet. That 4 models including VTG16, VTG19, Inception version 3, and Inception version 4. The result of experiment 2 shown in table 5. The MobileNet still be the winner in our VT81 dataset, even it comes with the lowest input resolution at 224. MobileNet gives us the highest accuracy with the lowest standard deviation compared to other 4 CNN. And also, MobileNet has the smallest size of the network. Not only for the accuracy, in table 6 show that MobileNet is also the fastest model compared to another 4. It using only 18.25 minutes on training time and 7 minutes 29 in testing. It means MobileNet is the fastest and the most accurate model between these 5 CNN in our vehicle type image recognition. Finally, the experiment 3. In this one, we change our input dataset to vehicle type image dataset 2 or VT82 to observe the effect of the larger data. For the method, this last experiment, we use our XCNN model that we mentioned earlier to find the champion model on our vehicle type image recognition. This X model, including MobileNet version 1 and version 2, Darknet 19 and 53, Inception version 3 and version 4, and Inception ResNet version 2. Moreover, we include the 5 data augmentation technique into our vehicle image dataset to find the best data augmentation technique that fit with our VT82 dataset. The result in table 7 confirm that MobileNet is still the best model for our vehicle type image recognition. It gave us the highest accuracy compared to other 7 CNN models, even with or without data augmentation. The second and third accurate model is MobileNet version 2 and Darknet 53. It might mean that our VTD dataset, or the dataset that comes with a few amount of data that's less than 10,000 images, should be more suitable to the small size CNN model such as MobileNet, not for the full size CNN model such as Inception or the ResNet. In case of data augmentation, we found that the best augmentation technique is the brightness, followed by the horizontal flip and the random shift. Because of these 3 techniques, won't lose any detail of the original image when it applies the augmentation. Unlike the other 2, the rotation and the zoom technique, these 2 techniques might lose some detail from the original data when it zooms the image or rotates the image. Also, If we compare the accuracy of vehicle image recognition on VTAD1 and VTAD2, we found that when we have lesser data, the accuracy has been increased. The accuracy on VTAD1 and MobileNet is 93.4, but for VTAD2 is 94.38%. In terms of speed, MobileNet version 1 might be a little bit slower than the MobileNet version 2. But if we counting the higher accuracy on MobileNet version 1, we still think that MobileNet version 1 is a good model to use in a vehicle type image recognition. Finally, the new confusion metric of VTAD2 with MobileNet architecture and brightness augmentation shown in Table 9. The accuracy of our 5 vehicle types are increasing, even the SUV. The prediction accuracy of SUV rise from 70% in VTAD1 into 88.23% for VTAD2. That confirms the effect of the larger dataset and the effect of data augmentation for the accuracy of image recognition. In conclusion, we found that MobileNet is the best, fastest, and smallest model, and outperforms other CNN in our VTAD1 and VTAD2 dataset for the vehicle type image recognition. Also, we found that the data augmentation has improved our vehicle type recognition result, with the best method is the brightest one. And with 2 datasets, we can confirm that the larger data has also improved the accuracy on the image recognition. This is all the result of our research in this paper. Thank you for your attention, and please feel free to have some comment or the question after this presentation. Thank you.